All right, today we are going to measure the speed of sound in air. So how we're going to do that? What we're going to do is we have a speaker here, and we're going to put out a short pulse of sound. And sound is just a pressure disturbance in air or water or any medium. So that sound is going to travel out, and eventually it's going to hit that microphone. Now I know, or I have placed these exactly 80 feet apart, measured with a long tape measure. So if I can measure the time between the time the pulse goes out here to the time it's received over here, I will then have the basic information needed in order to do the calculation. Now it's a pretty warm day, it's about 85 degrees and it's pretty humid. So air temperature and humidity will, as that varies, the speed of sound in air will also vary. I'd like to come back in the wintertime when it's about 20 degrees and do this same test and see if we can see the difference. I think we would. It's not going to be a lot, but it will be slightly different. So that's what we're going to try to do today. So one of the first things we're going to need to do is generate a pulse of sound. I wouldn't expect everybody to understand what's going on here, but I use MATLAB. If you're an engineering, math, science type, you may have heard of that. It's an excellent program for cooking up waveforms. What I did is I generated this waveform, and it consists of 5 cycles of 2,205 hertz and then nothing. So that's the waveform that I generated that we're going to use as our sound pulse. And MATLAB has a really nice feature called Audio Write, which you can take these waveforms and convert them to WAV file, which I did, and I burned it to a CD, and basically I'm going to play it through a CD player into an amplifier. What equipment are we going to need to do this? Probably the most important piece is an oscilloscope. This is a device that allows electrical signals to be displayed as amplitude versus time. So we're going to use this to actually measure our waveforms, outgoing and what's picked up by the microphone. So over here I've got a DVD player which will play a CD. So I've got the CD in there that has the pulse on it, and then we're going to play that pulse. It's going to go into this amplifier, and then that's going to go out to a speaker. So here we have a speaker that's going to produce the sound that we've generated. And if you follow over here, I've got a microphone set up. This is going to be used to pick up our sound, the pulse that comes out of the speaker. And if you look down here, I got it 80 feet measured out, and that's from the tip of the microphone basically to the front cone of the speaker. Now the sound, the electrical signal that comes out of a microphone is probably, I'd have to run the numbers, but it's probably close to 1,000,000 times weaker than what we're going to put into the speaker. So the microphone is actually plugged in here where we can bring the signal level up enough so that the oscilloscope can see it easily. This is a 4-channel scope. I'm only using 2 channels. The first channel is going to capture the waveform that comes out of the CD player, which is basically the same as what is applied to the amplifier of the speaker. And then channel 2 is the microphone output. So when we run this test, basically I'm going to come over here and press play. And then we're going to see a capture. So what do we have here? Over here in yellow, you can see that's the pulse that went out. That's the signal that's on the CD that we generated. That got played through the CD player, through the amplifier, and was applied to the speaker. Now the microphone is set up 80 feet away, so the microphone's signal is over here, and that's in blue. That's on channel 2. Now if you're wondering why it doesn't look the same, there's a number of reasons. For one reason, there's reverb, and the speakers aren't perfect. Even if you apply a pulse to them, they're still going to ring for a little bit afterwards, just from echoes around the yard. So you're always going to get some of that. So what we need to do is measure the time difference between these two. So first thing we're going to do is I'm going to use my cursors,
and I want horizontal bars. So this is going to give me the ability to measure the time delay. So you can see that cursor there moving. What I want to do is I'm going to magnify. So it's actually over on the blue one right now, so I'm going to move this way over. You see the window here is moving, and it will come over eventually to the trigger point. Turn that brightness up some. Alright, so what I want to do is I want to bring this into the display, and here you can see the pulse going out. This is what went out. It's actually very clear here. So what we want to do is we want to put this cursor just when that waveform starts to rise. So that's our starting point. That is what was applied to the speaker. So now we're going to go back over, move this window back over to this waveform, which is our output. Alright, so now we're going to be coming up, and now you can see channel 2. This is the output. So what we want to do is I'm going to select the other cursor, and now that one's highlighted. We're going to move that so it's right where that thing starts to rise. So both cursors now are precisely set at the points where the waveforms start to rise. So we're going to change. We don't need that magnification anymore. So those cursors are now representative of the time between these pulses. So if we look up here, we see 70.2 milliseconds delta between those two pulses. So using that number, that basically is the amount of time from the start of the pulse at the speaker to the sound received at the microphone. So we know that's 70.2 milliseconds to go 80 feet.
Okay, so now we are going to do some analysis with the data that we took. So earlier with the equipment, we measured that it took 70.2 milliseconds for the sound to go 80 feet. And that in seconds is 0.0702 seconds. So how long would it take sound to go 1 foot if it took that long to go 80 feet? So fairly straightforward calculation. You just take 0.0702 and divide it by 80. Spreadsheet's done that calculation for us right here. It's about 878 microseconds. But now we want to know how far would sound go in 1 second. So another fairly straightforward calculation. You divide 1 by the 878 micro, and you come out to 1,140 feet per second, rounded off. Okay, if I come over here to Google and I look up speed of sound in air in feet per second, we're going to see down here now they're doing it at 68 degrees, which is definitely about 20 degrees colder than what we did it at, and 343 meters per second, which comes out to 1,125 feet per second, right there. So let's go back to the spreadsheet, and they're saying 1125. So as you can see, that's pretty close to 1140. If we want to get a rough percentage, we would divide this by that, and you technically would multiply that by 100, but you can do that in my head easily enough. It's 98.7% of the value that Google is showing. But again, that was at a different temperature. So I'd like to run this again in the wintertime when it's cold, and I bet you we'll get a slightly different number for the same setup. So this tech session basically demonstrated measuring the speed of sound in air in feet per second, and we get a number that's pretty close, so it worked out well. I hope this session was useful, and there will be more sessions on different topics coming up, so check back from time to time.